Welcome to the webinar on the subject of interfaces between simulation and injection molding machines. My name is Max Mades, and I will hopefully tear down the walls between the shop floor and engineering with you today. If you have any questions during the webinar, please use the chat function or the question and answering function in Zoom and ask them. There will be time at the end of the webinar to answer all your questions, so you can either tell them or ask them directly, or we will talk about them at the end of the webinar. The topic from today is the interfaces between simulation and injection molding machines. I would like to talk to you today about possible applications and typical challenges on the shop floor where the use of simulation can be useful and provides real added value. Then I will show you in CADMould where you can find these interfaces and how they are used, where they are, how they are used. And at the end, there will be the possibility to ask all the questions regarding machine interfaces, everything you don't want to ask in between. The topic of communication between engineering and the shop floor is like a game of silence or the telephone game in lots of companies. It's a children's game where one person tells the next person, and some information is lost on the way. And sometimes it's really funny what's getting out, but on a corporate level, it's not very funny if something else arrives at the shop floor than was planned in engineering. Some sit in the ivory tower, the engineering department, and they get it running, and then they give it to the machine operator, who then starts over again and has to set up the machine. By bringing the two worlds together, many advantages and synergies can be used, and it will also bring simulation and machine closer together. We have therefore developed digital connections to the machines with Engel and ARBUG machines, which should simplify these communication channels and both bring the knowledge to the machine and also the way back, find the way back into engineering, into the engineering department, so that the engineering does not stop at the component development or the mold making, but also later when the production is already running, there is feedback for the production for the engineering department, so they can have feedback directly from the machine as well. At Engel or with the Engel machines, this works over the Simlink platform, where most of the machines which are included into the Simlink platform can be used and connected via the Simlink platform with the simulation machine and the machine. The simulation software in the machine. With ARBUG, there's a direct connection to the machine via the ARBUG Fill Assist module. It's on the machine itself and then translates the machine injection parameters to pre-optimized parameters on the machine. This is currently only available on Gestica systems. So only if you have the newest Gestica control on the ARBUG machine, then you can use the ARBUG Fill Assist and then have this connection readily available. On the shop floor, there are some challenges where simulation can be used. Here is a short overview with basically 3 topics. As a first step, or it's the choice of the machine, which, for example, if you want to choose the right machine for your part, you mostly have to look at parts like look at forces like the clamping force or the metering volume or the dosage volume of the part. Simulation can help you, or this is one of the challenges which come up if you start the trial runs or the setup of the machine. So which machine do I use? The second challenge where you can use simulation is the part itself. So with the In order to get to know the component better, filling and pressure can be examined and adjusted. And the injection profile, switchover point, and packing pressure profile can be looked upon and optimized. And finally, the tool itself can also be optimally adjusted and the cycle time optimized. In the following, we will go through the individual examples in a very practical way on how to do it without or better with simulation. Let's start at the beginning. When choosing a machine, a big factor is the required clamping force. Calculating this manually is a very high manual effort, costs time and nerves, and is very error prone. In addition, this is often necessary to go into the engineering anyway, because for knowing all the information or any key points for the calculation at all, you need to get some information from engineering department. If the clamping force selected is too low, there can be overspray or flash and potential damage to the mold. And if it's too high, there's an unnecessary wear of mold and machine, an unnecessarily high energy consumption, and there might even be burn marks on the part itself due to the trapped air. Nevertheless, shooting power that is too high is normally better, or usually better, than the one that is too low, because the mold doesn't get as damaged. And so it is simply closed, mostly it's simply set up this way. So as much as the machine permits, then they use a higher clamping force than strictly necessary. And especially in times of high energy prices and also ecological aspects, a lot of potential is lost here if the clamping force is just set to the maximum it permits, but not optimally set up. So instead of proceeding with a manual determination as before and using, for example, the rules of thumbs to specify the clamping force, or really experimentation where one gradually reduces the clamping force until the mold opens, or even using measurement devices where you have to set up all these dials and measurement devices to see how big my clamping force actually is set up. It is better to do it with simulation. In CADMould, the required clamping force has been simulated over the cycle of, is available as a result already for a lot of years. So you can see directly in the injection molding process where how high the clamping force is during the filling peak, and also during the packing phase. This allows you to go to smaller machine this allows you to go to a smaller machine, which is optimally using the clamping force which is really needed for the part. Yeah, so this is so that the clamping force is sufficient but not higher than necessary. The second issue is when you get a component. The second issue when you get a component is finding the correct metering volume. The question is, how big is the component actually? How much material goes in there and how is it distributed? How do users do that without simulation? They also go into engineering and ask what is the volume of the component, and based on this they start with a rough estimate and then start approaching with filling studies, where they increase the injected volume cubic centimeter by cubic centimeter, and then get somewhere to 80–90% filling. If the first shot already is a very short shot, and if it's not, if you start too small here, it may be that the ejector pins is not overflown or are not overflown during the filling study, and then it has to be mined out of the mold, and this takes a lot of time and can also damage the mold. Going too high, too fast can overload the tool or the mold and create burns that can also damage the tool. or it might even lead to breaking or bending thin cores inside the mold. So you also don't want to have a too high dosage volume or metering volume. It is much better to use the simulation. The filling behavior and setting are already set in the simulation and can be sent to the machine. Shown here in the Arbok Fill Assist on the left side in the video that's playing with the finger there. You can see that by using this slider, you can see how much the filling level is inside the mold, and if you know where your ejector pins are, then you can see where to start with your filling study. So it can be recognized directly for the different fill levels whether the ejector pins are sufficiently overflowed, and it is or the mold will be able to demold, so the part is falling out nicely. This means that trials and setup trials are less nerve-wracking, and expensive errors can be avoided. It is also possible to automatically set up the first set of parameters for the injection units. So they are dependent on the material, molded part, and machine data. The stored databases and algorithms replace the usual manuals where you have to look it up in a book or in different kind of sources, and it all comes from the simulation where these informations are stored, bundled together, and then given to the machine. You also don't have, they are sent directly to the machine, so you don't have to manually fill out some kind of setup sheet from where you have to walk with a paper to the machine and put all of them in, which might also lead to user error. In order to get to know the components, so this was mostly machine setup. Now how to specify the part which you want to fill inside the mold. In order to get to know the component, injection profiles can also be run in addition to just the dosing volume. In order to run components optimally. So a lot of people just use one or maybe two speeds, but if you really want to get to know a part, you can also play around with the injection profiles, or you can optimize the part with the injection profiles so that the steps where, for example, wet lines might occur, or the runner goes into the part, so that it's filling faster at these steps. This raises the question, when should these steps be installed? For example, for the weld lines, and these must be brought then to the machine. A profile on the left side, the line you can see here is from the simulation optimized filling profile according to a what is called a flow front. So the flow front always has the same speed. And you can imagine either determining this on the machine in trials is very tedious. And if you want to bring this to the machine via a sheet of paper, that's also a lot of input. So just with the connection between simulation and the machine, this can be way quicker and done without error-prone conversions. This process of the injection profile to optimize it, it works better with simulation. With a simulative optimization, you start somewhere else than on a green field or on a green meadow, where you can run significantly fewer real tests to break in your tool, or to try to first run your tool. In addition, profiles are transmitted digitally, which means that no manual transmission and typing is required. The fine adjustment on the machine still has to be made, so there still have to be some trials at the machine, but you can focus much more quickly on critical areas because you know where critical areas are on your part. So for example, if you have a weld line somewhere on the part and with specific kind of parameters they can be avoided, then you also don't just to look at this part of the part itself, and not have to do a full setup or trial run. So yeah, the trials and the blocked machine time just for the breaking in or the trials of the mold, the first trial of the mold, is much quicker. This yeah, leads to faster sampling and shorter machine times, and also material costs. When you have completed the filling study just for the filling of the mold, the next question is, how do I determine the correct switchover point? Without simulation, this is based on rules of thumbs, where you normally use yeah, the knowledge of the user or the machine operator, and this sometimes leads to not optimal results, where the results mostly are, yeah, it is fine this way, but not yeah, really optimized. Or you can either use the machine operator's knowledge, or you can have lots of real trials where a lot of material and time is wasted. Yeah, to use a short analogy, it's like lowering the landing gear of a plane without knowing the height above ground. So you know you want to land, and you know sometimes you will touch down, but you don't know when to lower the landing gear. In CADMould, you can already see approximately how far the filling will have progressed and when, and what's the filling behavior of the part. In this way, you can ensure that you have at least overflowed the injectors on your first attempt, then carry out first real filling study and compare it to the simulation. And if there's a good match, you can trust the simulation well and look for a good point, or you can optimize it in the virtual world, and then go to the machine and yeah, have your tryouts very much faster, or yeah, quite faster. And there's a fewer real world tries needed with better results than if you would do it by hand. How to yeah, for the packing, a third point, which is more with some in reality, it's oftentimes overlooked because it takes a lot of time and is very complex topic on top of the injection profile, is the packing profile. And many molders avoid using packing profiles altogether because of the complexity. And how would a packing profile, or how could packing profile improve the results, is often not even asked, because it's too much hassle to actually set up. And from a yeah, simulation standpoint of view, this is a waste of potential, because with a packing profile, there can also a lot of work be done. And yeah, this is why by hand I can understand that it's a lot of it's very complex, this topic, but from simulation it's very good to also keep this in mind. So how do we do this with simulation? With a simulation, you would you could set it up in a Varimos virtual optimization tool, and you automatically simulate and analyze a lot of profiles with different parameters using the Varimos module. Then you generate a suggestion for optimal packing profile, send this to the machine, and then yeah, start your tryouts there. Maybe adjust it a little bit, but this is then a good starting point, and you can really use the packing phase as well, and not only injection phase and yeah, just one set of packing. The third part would be to look at the cooling system or the cooling time, and get to know the mold itself better after machine and the part. Then you can also take into consideration that the mold with the cooling system, and to set this up in a workflow without simulation. One of the big questions asked here is, how long should I cool to ensure safe ejection? Yeah, so that the part doesn't demold, so the ejector pins don't leave any marks on the part. And the workflow without simulation would be just a starting point according to wall thickness of the part, the biggest wall thickness. There's this rule of thumb, the mass temperature, material type, etc. And then do a lot of trials to locate final values where you reduce the cooling times until the final value is reached. This also takes into account that you hope basically that the mold is goodly is well built and the cooling inside the mold is uniform. The manual setup of the cooling parameters can be accelerated or much better simulated with a tool. With simulation, it is possible to have the simulation in advance, and parameters and cooling time can be set up. It can also be simulated how long it takes until a stable kind of state is reached. So if you have the tryouts by hand, you always have to wait until the mold gets to a stable point again. And with the simulation, you can see, for example, in the picture shown here, that after 10 cycles or something, that the mold reaches a stable state. They can then also be sent digitally to the machine, which also leads to fewer tryouts for the fine adjustment. Or just a few parameters which you have to set up in your periphery machines, like temperature, the cooling temperatures units, cooling units. They still have to sometimes be put in hand because they don't speak to the machine directly, at least not in all cases. Some cases do, some cases don't. The advantages of this is that the starting point is already pre-optimized with the simulation, so you don't start at the material data, for example. This reduces also the number of trials until the final optimum is reached. And it has consequently less waste of material, energy, and time again. The manual inputs are also reduced, not completely erased as with other parameters, because sometimes you still have, like I said, the machines don't speak to the cooling units, but the starting values are from the simulation. You just have to put them in there. Maybe in the future. So to sum up again with the simulation between the digital connectivity between simulation and machine, it is possible that the simulation can speak directly to the machine and also the way back, that the parameters from the machine reach back into the simulation. This means there's a direct availability of simulation data on the machine, and this enables faster and more efficient machine setup. One important point to state is that the machine operator remains fully in charge and makes the final decisions. So it's more of suggestions as not as a hard that they are forced to use the parameters from the simulation, but the machine operator starts from a better point and can focus more on optimizing and improving than first finding a stable kind of point where to start with the optimization. The next part is a part where I want to show you live in CADMould where the connectivity modules are found. And for this, I will go to CADMould. And here under Start and then Machine Interface, you can find the buttons for Symlink and ABOK Fill Assist. The Symlink import uses, if you press it from the Symlink you can export these profiles from a exchange format. Then you just have to open it. And it creates a new ID for the simulation where there's some kind of Symlink nodes where it says, okay, this is a screw diameter, this is the machine used inside of Symlink, and some kind of other information. And if you use this, I go to an unused ID. If you go to an unused ID, then you create this. Then you have imported the machine settings, how it is, how it was at the machine, or how this part was made at the machine. If I go to simulation process parameters, and then in the filling time, I can see my filling profile. And this is, for example, the profile which was then imported directly from the machine with some kind of delay times where the machine needs some kind of time to switch from one point of this to the next for the injection profile. Yes, the same is true for the packing. I will show you this later or after this. But there's a second button which is new in CADMould, which I want to make as a quick excursion, where you can, instead of this profile, which is then how it was at the machine, you can also do something like, if you have a part where you don't know the profile yet, you can also have a constant flow front speed. And this is then calculated via either previously run simulation or just based on the part geometry, where you have some kind of flow front or profile, how it should be driven so that the flow front always has the same speed. If you go to the packing, you can also see in this trial there wasn't much of a profile made here, but you can see that at least the from the injection pressure down to the packing pressure, and this is the profile which was then run at the machine. If you want to export your data, you also go to machine interface and export via the RBOK button. This is then not used with Symlink, but with RBOK. And if you press on it, it will create a file, a zip file, which will then be shown here in the middle, where it creates all the necessary files needed for for input at the machine. So you then can take this zip file, go with this to the machine, load it there, and have all the necessary data available at the machine. So to view the data on your fillises, please unzip the file and then load it into your machine. What is inside this machine is basically just a few files, which are already in a normal simulation folder. There's a lot of files, but if you go to the zip file, which was just created, is basically just the RM1 file, two kinds of result files, and a file with an older version. This is the 14K. If you have some kind of problems regarding if you, for example, if you use a newer version from CADMould and it's not compatible with your RBOK machine, then you can try to use this older version, this which is also delivered inside this zip file or from this ARBOC export button. Yes, first you have to rename it to RM1, of course. Okay, so then back to the okay. All right. For the to sum up, the development process mostly as shown here with the part design, the mold design, and virtual parameter optimization. In these steps, the engineering aligns with the machine, or it develops the part, develops the mold, develops or chooses the right machine, and then gives this for the mold makers to build the mold and hold the tryouts, and then at least at the end go to serial productions. These steps require or encourage a lossless digital transfer, so that all the information which are done in the engineering department go to the machine operator and get to the machine. One big step or one big next step would be that the results at the machine tryouts go back to the engineering, so they can share the results and then maybe also share the final parameters. And what would be really good is that this already takes place during the first development of this part, so that the engineer already in this stage maybe talks to the machine operators and knows what to keep in mind, so that both ways talk to each other. So it is a back and forth of information sharing, and that communication really is encouraged inside of a company. This, if done correctly, could lead to a lot of advantages for the company, which are shown here with improved quality, reduced cost, a shorter time to market, better teamwork inside the company, and enhanced sustainability, because a lot less material is used in tryouts, a lot less machine time is unnecessarily blocked, and can be it has a lot of advantages if all the communications really talk to each other and make full use of a connection between simulation and machine. Now I'm coming closely to the end. I would like for all of you maybe to fill out a quick survey, just as a feedback, and after this there will be the possibility to ask questions, and I will answer as best as I can. All right. Yeah, for this question, which is shown right now, it is also possible to have multiple answers. Yes. Yeah. If you're done with that, are there any questions regarding machine interfaces and whatever? There is one question which says, what are the limitations? Limitations regarding to what? Currently, like I said, we have the simulation with ARBOC and Engel, which are two machine providers. there are currently some kind of limitations still to be found out, and it's hard to say what are the limitations in general. Some kind of special processes currently are still not supported, or very complex tools. But in general, this is already running, so it can be used, and the use cases, they get more from day to day, and a lot of people already are using it, and we're getting more and more feedback on how this works. That it actually works is also good feedback. Then that people say, yeah, we can reduce our setup time significantly using this. Lots of people are very fond of this. Others still are more skeptical, but yeah. Another question is it possible to define the injection profile in millimeters? Screw position like the injection machine. It is possible for the if you have, for example, with the Engel machines, the translation from the simulation parameters to machine settings, which are actually put into the machine, is done in this Simlink portal, where the Simlink, you can open a software or a simulation, and the actual settings are then translated to the machine. The same with ARBURG. In ARBURG, when you give a simulation to the ARBURG machine, it internally translates to all the parameters which need to be set up for the machine. So you actually, you just set up the simulation and then give it to the machine, and it translates to everything you need to set up. Do you think you can add a machine database with time response, screw diameter, max clamping force, volume, and max pressure? This is one question where, if I understand correctly, that there would be a machine database inside of CADMould. This is probably not really going to happen, because it's a lot of work with the machine providers itself. So they have to update it, and sometimes they are really made for the customer itself. What could be possible is that there is some kind of company internally machine database where you can internally use your machine data, your machine catalog, which you have inside your machine. With a Simlink portal, you can select most of the machine in the Engel world, basically, and then you have some kind of machine database inside of this Simlink portal. Yes, so on this side, it would be there. The next question would be, how would you use imported machine curves? This would be mostly used, like I have shown, in the injection profile. So you can see if there are some kind of response times. So normally, if you set up a simulation, it goes directly from one step to the next, but the machine sometimes takes a bit from one step to the next. So with this, you can actually see these response timers and how long it takes from one step to the next. So in the filling profile or the packing profile, they would be used. Will it be possible to get the data in a data sheet instead of a file? Is a next question. I'm not really sure if I understand the machine, the question, but for the exchange format, it basically is some kind of data which comes from the simulation to the machine, and they are written inside in some kind of file. We don't have any printout where you can look it up at some kind of specific format. So you just go with a paper to the machine, but in general, it could be done quite easily. Yes. Is it possible to transfer simulation data in all ARBUC and Engel, or is it only for specific variants? For the Engel machines, it's basically all machines which are used in the Simlink. And for ARBUC machines, you need the fill assist, which is currently only available with the Gestica control system. So it is not possible to go to all ARBUC machines, but yeah, most of the newer ones, they can have this ARBUC fill assist module. And for the Engel machines, every Engel machine which is connected to the Simlink portal, which is yeah, the portal from Engel itself, they can be used, as far as I know, which is mostly all of them, or most of them. Okay. If there are no further questions, I would like to thank you for your time, that you are interested in this topic. Yeah, please come again and watch our webinars or contact us for yeah, anything else you need, any other questions regarding CADMould, Varimos, or yeah, what we do at SimCon. Thank you all, and have a good day.